we also looked into how to develop some very simple MLP for doing image classification, and we learned the basics of how to implement some neural networks. Now let's try to learn some additional techniques that is good for regularization, which is an ability that your neural network can generalize to a more wide type of data. We can also do some regularization, increase regularization by doing data augmentation. So when we're doing data augmentation is we are trying to obtain some big data from a small data. And this data augmentation is the simplest way to reduce overfitting to increase the size of the training data, which means that if we have this single image currently, we can try to make this image in different shapes, rotate these, shift these, and change the directions, etc. So, for example, we can shift our image, shear our image, shift and scale our image, rotate and scale our image, and generate various data, which is also a data of cats. So even from this single data sample, we have generated how many is this? This is 15 data samples, more data samples, and therefore, for example, this will increase significantly the amount of data samples we have, and then the neural network will be able to look into more data and will lead to better generalization or regularization. Also, a technique called early stopping is important because we don't want to have overfitting in our network. However, our neural network is designed to minimize our training loss as much as possible. So this frequently happens. For example, here, if you look into this graph here, the y-axis is error and this is training steps. Our training error will decrease continuously, because we are minimizing the training loss, and the neural network is looking into the data and is kind of being fitted in those data continuously. However, if we also evaluate our validation error in our validation data samples, we can see that the validation errors are decreasing to some point, but however, this will increase again. And which means that our model is overfitting to the training data sample. We don't want overfitting because what we want is to have good performance in a totally new test data sample. So what we need to do is we need to stop our training in some point, and we can do this by early stopping by measuring or monitoring the training error and validation error and see if your training error is decreasing, and if your validation is now increasing, then you can stop here in this training step here. Dropout is a very famous method to regularize your neural network. So what it does is, at every training iteration, it randomly selects some nodes and then remove it. So which means that if this is a standard neural network, in some iteration, this will remove some nodes here, which means that it's removing, it's freezing these weights here. It's not training these weights. So this is one example, and in another iteration, we can also delete another nodes. For example, this one, and this one. Anything can happen in these dropout layers. So this can also think that we are training many different types of neural networks at once. Or you can think this as an ensemble technique in machine learning. So to take a look in this dropout as an illustration, as I told you right before, it's a different architecture at every training epoch. And so therefore, if we have our original model like this one, for example, in iteration 1, this will be dropped out. Let's say that this happened. And you can also easily implement this by this one. Transfer flow and n dropout layer, and this rate p, this is the probability that each element is dropped. So for example, if we set this as 0.1, this would drop 10% of the input elements. So for example, if we define some dropout layer right here, then with 10% of probability, an element will be dropped out. So for training, in this training stage, this dropout layer, we need to input some rate of it, which was the probability, which I just explained in the previous slide, that each element is dropped. So yeah, depending on this rate, the probability of dropping out an element will be determined. And with this probability rate, one important thing that we need to do in the training stage is that we need to scale the inputs by 1 divided by 1 minus rate. So by using the scaling, we can make the expected sum unchanged. So by using this one, we're going to have some consistent prediction. And for testing, we are keeping all of the elements. We're not dropping out any elements here. And we're using all of the weights. So then this will be some kind of like an ensemble network which was trained with many different data samples and many different models. And by using this testing with all of these elements, then we're going to be able to predict a result with better regularization. And this is also possible because we have scaled up our inputs by this in the training stage. Otherwise, we're going to have a very large prediction in the testing stage. However, you don't need to really be worried of implementing these because we all have these functions already inside Keras. So when we're implementing dropout using Keras, you can see that here we have dropout layer, dropout, dropout, dropout. You can just add these dropout layers right after your dense layer, the fully connected layers of your neurons. So here, 0.2, 20%, 20%, 20%, 20%. And here this will have like 30 units will, out of 30 units, 20% of them will be dropped out of 120%, and so on. So that's all. That's everything that you need to do if you want to implement this dropout layer. So it's very convenient. Everything is already implemented very well in Keras. Another technique that I would like to talk is batch normalization. So batch normalization is a well-known technique to improve the performance and stability of your neural network. And this is because it normalizes the layers by adjusting and scaling the activations. For example, if you have some inputs like this one, activation inputs, or you can think this as some output or your outputs in your neurons, you're going to scale these into some small, some tight range inside here. So what happens if we do this is, for example, if we're using sigmoid activation functions, if we have for this original activation inputs here, these red lines are actually the gradients of sigmoids. So we're going to have very small gradients in these inputs here. But however, if we scale our inputs to this range, we are all going to have some good gradients here so we can train our neural network much better. And this is what batch normalization does in every layer that you determine to do this batch normalization. So you can also think this as doing some feature scaling. Feature scaling is important because we are trying to make different features to have the same scaling, and this actually helps doing the learning. So for example, if your x1 and x2, let's say that these are the input features you have, and the scale of your x is 1, 2, and the scale of your x2 is 100 and 200, and if you're trying to train your weights here, it could be kind of difficult because your scale are too different. Then you're going to also have different weights, different scales in the weights, and these will make it hard on the network to update correctly. However, if you match these by some scaling to have some similar scales, your network will be much more comfortable to update your weights more easily. so you can have a better regularization result. And to talk about the implementation and the algorithm here, the algorithm is simple. You just need to shift and rescale according to the mean and variance on the batch of your data. So if you have your mini batch, which we are using in training, you calculate the mean of this mini batch and you calculate the variance of this mini batch. And then what you do is you do something similar to standard scaler. You normalize this xi, and you also can scale this as this one here. So this is how you do batch normalization and during your training step. However, in your testing set, you should not use the statistics from your training data, from your test data samples. You need to use the statistics, the mean and variance that were estimated in your training data sample. So during the testing step, you can just simply shift and rescale your layers according to the empirical moments estimated during training. So to implement this in Python, you can see that this is our base model. And for example, if we want to add batch normalization, you just need to add it like this one. Something that like you have done in your dropout layers. Just add it after your dense layers. And what happens here is they calculate these means and variance and do the rescaling in each layer and try to make your layers more trainable. So all of these regularization techniques that we discussed in this lecture are all also provided in Keras code in Python in your IPython notebook file. So please take a look into that file and try to run all of these regularization techniques by yourself. So to sum up, we learned artificial neural networks. And these artificial neural networks are complex or nonlinear universal function approximator. We can approximate any kind of functions using multi-layer perceptrons theoretically. So these multi-layer perceptrons or artificial neural networks are composed of linearly connected networks, the weights and biases, and some nonlinear neurons with nonlinear activation functions. So using these artificial neural networks, we can do some classification problem. For example, class 1, class 2 with any kind of input data. And what this neural network does is it first learns the features in the first until the last layer, and then it does classification in the last layers here. This could also be regression if we are doing a regression problem. So these are what artificial neural networks are doing. And when we're doing a deep artificial neural networks, it means that we are adding more and more layers. There's no specific rule of what is deep or not, but usually it's about like 10. If it's deeper than 10 layers, we call it as a deep artificial neural networks. In deep artificial neural networks is more capable of learning more complex and nonlinear functions. So which means that we can extract some very good features. We are extracting features here. This is what your artificial neural network is doing. And based on this extracted feature, we can do very simple classification or regression by adding 1 or 2 layers here. So that's what we do in deep artificial neural networks. So at last, let's also talk about the difference between machine learning and deep learning. So for conventional machine learning, this is a category where we are doing feature engineering. Human is doing feature engineering. We are informing our machine learning model about the important features that we have here. However, in deep learning, we are letting our neural network model to learn about the feature itself. So this is doing feature learning. So the network is extracting the feature by itself and doing some classification and regression, which is different with this one. When we're doing feature engineering, we provide the information of the feature. For example, this feature contains some sine function, or this feature contains some cosine function, or anything else. So deep learning and machine learning are kind of different. However, these two are both very important, because in many engineering cases, we don't have enough data. And in these cases, we of course need to provide some information, our physical knowledge of the features that our data has. And in those cases, these feature engineering will provide many advantages to our machine learning model to learn well inside our engineering data. When we have a lot of data, some sufficient amount of data, then we are able to let our machine to learn the feature itself. And that's where we can utilize deep learning. So both machine learning and deep learning are very important. And in the following classes, you're also going to learn more deeper about deep learning. So that's all for the artificial neural networks.